There is an assumption that the primary financial hurdle in artificial intelligence is the hardware required for initial model training runs. Once a model finishes its final epoch and is compiled, the vast majority of capital expenditure actually shifts toward deployment. This deployment phase is called inference, the continuous process where a trained model receives user inputs and generates outputs. If you are building a conversational chatbot, operating a retrieval-augmented generation pipeline against private documents, or deploying autonomous agents, you are running inference workloads. The underlying math creates a massive scaling problem. A multi-million-dollar training run is an isolated, one-time cost, but inference infrastructure has to expand to match concurrent user demand. For an AI application to survive economically, engineers have to figure out how to shrink the physical hardware footprint required during this phase. Let's isolate the root of this bottleneck down to the atomic unit, the individual model parameter. Over the last few years, state-of-the-art models have scaled upward from billions of parameters to hundreds of billions, and now reach into the trillions. To process a query, every single one of those parameters must be loaded into the physical memory of a GPU, known as VRAM. This introduces a strict deployment limit. If the total data weight of a model's parameters exceeds the VRAM capacity of a single GPU, the workload splits across multiple hardware nodes. Left unoptimized, the raw mathematical volume of a modern large language model makes it too expensive for widespread production use. To see how this breaks down in practice, we can look at the Llama 4 Maverick model, which contains 400 billion parameters. It is released in a native, uncompressed precision format called bfloat16. At this precision, every individual parameter requires exactly 2 bytes of storage. Multiplying the 400 billion parameters by the 2-byte depth yields a base requirement of 800 gigabytes of VRAM. High-end hardware operates at an 80 gigabyte limit per card. To fit this model, we must stretch it across 5 separate A100 GPUs. At roughly $10,000 per card, requiring 5 discrete GPUs just to house the baseline weights destroys the unit economics of a deployment. Even scaling down to a smaller enterprise target, like the Llama 4 Scout model at 109 billion parameters, does not resolve the issue. The Scout model's native bfloat16 footprint requires 220 gigabytes of VRAM, forcing a baseline infrastructure of at least 3 80 gigabyte cards. Because even these 100 billion parameter systems shatter the single-node deployment boundary, engineers have to structurally alter the data format itself. The standard machine learning solution to reduce this mass is called quantization, which systematically lowers the numerical precision of the model. Using algorithms like sparse-GPT or GPTQ, engineers apply smart scaling techniques that map complex 16-bit float values into tighter, lower-precision numerical constraints. If we take the 109 billion parameter Scout model and convert it to an INT8 format, an 8-bit integer, we cut the weight of every parameter in half, taking it from 2 bytes to 1. This diagram shows how the model's physical footprint compresses. The total data volume drops from 220 gigabytes down to a dense 109 gigabytes. At 109 gigabytes, the model now fits cleanly inside a dual-card cluster. By mathematically halving the byte depth, we entirely eliminate a $10,000 GPU from the required architecture, altering the financial math of the operation. We can push this compression limit even further by stepping down to an INT4, or 4-bit integer format. At INT4, the storage cost drops to exactly half a byte per parameter. This shrinks the final footprint to 55 gigabytes, allowing a massive model to slot neatly into a single 80 gigabyte GPU. This is critical as it leaves 25 gigabytes of overhead memory free for the KV cache and operational space. Reducing the model's footprint alleviates the memory bandwidth bottleneck inside the GPU itself, where moving data between memory and cores is the primary speed constraint. Operating within INT4 can drive a 5-time increase in the model's throughput, allowing it to output significantly more tokens per second. Optimal quantization reduces the required hardware infrastructure by 2/3, while simultaneously multiplying the speed at which users receive their generated responses. The major architectural concern here is that stripping away this much numerical precision will permanently destroy the complex reasoning capabilities of the model. Engineers at Red Hat tested this exact trade-off by running 500,000 individual evaluations on quantized models. They pushed these compressed models through rigorous industry benchmarks like AMI and GPQA to assess logic and complex reasoning. This chart illustrates the evaluation results. Moving from native bfloat 16 to an int4 compression resulted in less than a 1% degradation in reasoning accuracy. The reason precision loss doesn't equal intelligence loss lies in how the math operates. Quantization acts as a regularization effect, smoothing out statistical noise stored inside the billions of weights. Compression in a large language model does not behave like traditional software compression. Shedding precision often strips away erratic numerical variables, acting as a behavioral stabilizer rather than a corrupter of logic. Integrating model compression into a production environment requires matching the specific mathematical schema to the intended workload. Online inference specifically covers real-time systems, things like user-facing chatbots, conversational agents, and extremely fast retrieval-augmented generation pipelines. For these specific workloads, minimizing latency is the primary metric, specifically optimizing the time to first token so the user feels immediate responsiveness. During online inference, individual user requests rarely saturate the total compute capacity of the GPU. The bottleneck is loading the data, not doing the math. The premier architectural solution for this is the W8A16 schema, which stands for Wait 8 Activation 16. This format ensures the heavy parameters load rapidly from memory as 8-bit values, while the actual runtime math, the activations, process in higher 16-bit precision. This asymmetrical approach balances delivery speeds with the high-quality text generation required for dynamic, user-facing applications. Offline inference pipelines typically handle massive asynchronous operations, like batch processing millions of transcribed customer calls for accurate sentiment analysis. In these scenarios, the GPU utilization profile changes entirely. The processors operate continuously at their absolute maximum compute capacity. Latency per request is irrelevant here. Because throughput is the goal, symmetric precision formats like floating point 8 or int8 are mathematically superior choices. Utilizing a symmetric precision format across both the weights and the activations allows the physical hardware to multiply its raw compute rate by up to 5 times. Engineers execute these configurations using modern MLOps frameworks, relying on tools like the open-source Hugging Face LLM compressor alongside engines like vLLM. A standard deployment pipeline involves importing a base model, running the appropriate quantization algorithm through the compressor, and serving it via a high-throughput API endpoint. Balancing bit depth against VRAM limits through this inference calculus allows engineers to transition generative AI from expensive laboratory experiments into financially viable enterprise architectures.